So this notebook was put together by myself and Maria, who will be presenting the Stage 3 pipeline. It's an overview of the steps that are applied for the Stage 2 pipeline for spectroscopic data only. This notebook is based on an original format by Brian Hilbert, so if you've been in any of the previous webinars, this may look familiar to you. Before we begin, just to point out some caveats about this notebook. As you may have gathered from James's presentation, the spectroscopic pipelines are very complex and have many steps that depend on the mode being used, and the paths that each step takes is very diverging. So it's not really feasible to run each step in order to illustrate how they work, because you need several different kinds of input data sets to do so. Instead, what we're hoping to do today with these Stage 2 and Stage 3 notebooks is illustrate how you could run the pipeline for each step and to explain in detail what each step is performing and how it's run. So we're not going to execute any of the cells in this notebook. They're just here for reference. A brief introduction into this pipeline. The Stage 2 spectroscopic pipeline is called CalWeb Spec2. I will be referring to it as the Spec2 pipeline from here on out. As input to the Spec2 pipeline, you must provide the slope image from stage 1. This is that cal file I mentioned before. It's a count rate image. As output, your main product will be the cal file. This is an unrectified but fully calibrated exposure. You also get some ancillary data sets, X1D files, which are your first preliminary versions of 1D spectra, and S2D and S3D files. These are 2D and 3D rectified products depending on if you're using an IFU mode or not. These are quick look products only, so don't use them for full scientific analysis. We'll get updated versions of them in Stage 3. James already went over all of the different spectroscopic modes, but you'll be seeing a lot of acronyms in this notebook, so they are redefined here for your convenience. NIRSpec fixed slit is FS. NIRSpec MOS, or multi-object spectroscopy, is also called MSA, or micro-shutter assembly, so you see those used interchangeably. NIRSpec IFU, integral field unit. MIRI, there's fixed slit and slitless modes of the low-resolution spectroscopy. And you also have MIRI MRS, medium resolution spectroscopy, again in IFU mode. NIRS, there's a single object slitless spectroscopy. And there's wide field slitless spectroscopy for both NIRS and NIRCam. So there's a lot of documentation and information in this notebook, which we're not going to go over, but please feel free to refer to this later if you want to remind yourself how to do any of these things, like install the pipeline, or how to run the pipeline. Briefly, I will mention, though, reference files. Calibration reference files are FITS or ASDF, ASDIF files that are used by the pipeline to either remove instrumental signatures, such as flat fielding, or to calibrate data, such as converting from count rate to flux. These files are stored on a system at STSCI called CRDS. Here's an example of how to import the Spec2 pipeline and how you could import each of its constituent steps. Again, we're not going to run this cell. It's just here so you know how to do it. Again, briefly, I'll explain a parameter reference files. These are files that you can use to define all non-standard parameters that you want to use when you're running the pipeline. If you want to turn a step off or change a particular parameter in a given step, you could specify it here. This is the section I mentioned about how to run the pipeline. It's very detailed and gives some examples, so we won't examine it in that much time right now. So let's start talking about the steps that are applied in the Spec2 pipeline. First and arguably most important is assigning the WCS. So this transforms positions in the detector frame to positions in a world coordinate system, including wavelength. The WCS information is saved in the ASDF extension of the FITS file, or you can access it and explore the information very easily if you load the FITS file as a data model. This step is applied to every mode and every instrument. Below each of the explanations of what the step is doing is a code cell which shows how you can define the step, modify any of its parameters, and then run it. Please don't run this cell, it's just here for reference. Next is the background subtraction step. By default, this is the background subtraction method used for almost all data types. You'll see that there are several different methods of performing the background subtraction as we go through both this notebook and the Stage 3 notebook. This is a very simplistic method. It just performs image from image subtraction. And for non-wide field slitless modes, you can provide the target exposure and one or more background exposures. If there's more than one background, you average them together first before subtracting. For wide field slitless exposures, you use a background reference image, which you scale and subtract from the science exposure. Next is the Imprint Subtraction step, which is only applied to NIRSpec, MSA, and IFU data. Because the MSA, or the micro shutter assembly, is not completely opaque, this allows some light to leak through and create patterns on the detector. You can remove this pattern, though, by subtracting a dedicated exposure that you've taken, which has all of the shutters closed and the IFU entrance blocked. So if you run this step, you input both your target exposure and this dedicated imprint exposure. Next is the MSA Flagging step, again applied only to NIRSpec, MSA, and IFU data. That micro shutter assembly has some shutters that are permanently failed open. It means they either don't close when commanded or they have no shutter door. And because of this, they're always open to the sky and they always acquire spectra. So this step will flag any pixels that are affected by open shutters. 2D extraction step. This is applied to NIRSpec fixed slit and MOS data and all wide field slitless data. You extract a 2D array or cutout from your spectral image across the science, error, DQ, and any variance arrays that are present in your dataset. You also compute an array of wavelengths that is associated with the along dispersion direction of the cutout. The source type determination step. So the pipeline will try to determine if the source in question should be considered point or extended, and based on that will populate the science extension source type keyword with either point, extended, or unknown. So for single source observations, the pipeline will use information that's been provided by the user in their APT program, where they can specify the source type. But if the user didn't specify that, then the pipeline will try to determine what it is based on the observing configuration. For NIRSpec MOS observations, which are multiple source observations, you can use the stellarity that's been supplied by the user in the MSA planning tool. And finally, for wide field slitless observations, you actually set the source type keyword to unknown in all cases, and instead you determine the source type based on the direct image source catalog that gets output when you process the direct image. The step is run for every mode and every instrument. So this is the first of some of these alternative background subtraction methods. This is the master background subtraction method. For the most part, this actually should be run in Stage 3. For NIRSpec MOS data, it gets run during Spec2 Pipeline. But the algorithm is the same. So what you do is you take a 1D background spectrum, interpolate it to the 2D space of the science image, and then subtract it. And this 1D background spectrum, you can either determine what it is on the fly, or it can be supplied by the user. So in this case, for NIRSpec MOS data, you could use, for instance, background slitlets. Wavelength correction step. This is only applied to NIRSpec fixed slit and MOS data. Pipeline will update the wavelength assignments for point sources that are known to be off-center in the dispersion direction. The exact methodology of this updating is described here, and I'll skip it in the interest of time. A flat field correction. So this flat field is the input science data set, usually by dividing by one set flat field reference image. However, for NIRSpec, the flat field varies with wavelength, and the wavelength of light that's falling on any given pixel depends on the mode in use and which slits are open. So instead, you construct a flat field on the fly by extracting relevant regions from several reference files. And this step is applied to every instrument, every mode. A stray light correction step. This is only applied to MIRI MRS channel 1 and 2 data. So the pipeline will identify which pixels belong to a slice and which pixels are located in the gaps between slices. These slice gap regions shouldn't be receiving any light from the sky, and therefore you can use pixels there to estimate the amount of stray light and the exposure, and therefore correct for that stray light. Fringe correction step, only applied to MIRI MRS data. This corrects the fringing in IFU data by dividing by a fringe reference file. Path loss correction step calculates and applies corrections that are needed to account for loss in signal. For NIRSpec, this accounts for light being scattered outside the grating and not passing through the aperture. For NIRSauce, it corrects for flux falling outside of the subarray. And those are the only two modes this is applied to. Bar shadow step. This is only done for NIRSpec, MSA, or MOS data, and only for extended sources only, since they're covered by multiple microshutters. This will calculate the correction that's needed to account for the bar that separates adjacent microshutters. The photon step. This applies a flux calibration, converting the data from count rate to either surface brightness or flux density. For NIRSpec and NIRSauce observations of point sources, your output will be flux density or megajanskis. All other data types, you get surface brightness in newtons megajansky per steradian. This is again applied to every data of all instruments and all types. The resample step resamples the 2D image based on WCS and distortion information. And it outputs an intermediate file, the S2D file that I mentioned at the beginning. And as a reminder, this is a quick look product only. And an updated version of this product will be created in the next pipeline stage. This step is applied to NIRSpec fixed slit, MOS, and MIRI fixed slit data. Cube building step. As you might imagine, this is only applied to MIRI and NIRSpec IFU modes. This corrects for distortion in each of the IFU slice spectra and then assembles them into a rectangular cube that has 3 axes, 2 spatial and 1 spectral. This step is actually run in both this pipeline and the Spec2 pipeline. The difference is the methodology of creating the cube and the input data exposures. So for Spec2, you're only calibrating 1 exposure at a time. And for MIRI, this means that data from different channels are included in a single exposure and therefore will be output in the cube with a non-linear wavelength dimension, meaning that it's discontinuous between the wavelength arrays. The output from this step is that quick look S3D file. This is a rectified 3D product. Finally, we have the 1D extraction step. So this will create a 1D spectrum based on your 2D or 3D data set and output that spectrum to another of these quick look products, either an X1D file for non-TSO modes or an X1D-INS file for TSO modes. You can also do another optional background subtraction method during this step. So for non-wide field slitless modes, you use a reference file to specify the location and size of the target extraction regions and the optional background extraction region. For wide field slitless modes, the extraction region is defined as the entire 2D subarray or cutout that was made for each source. And to build on that, for non-IFU data, you use a rectangular aperture, and for IFU point sources, you perform circular aperture photometry, and you can again supply an optional background annulus. For IFU extended sources, you use rectangular aperture photometry over the entire image, and therefore you don't estimate any background. For most modes, you also perform a correction to put the results on an infinite aperture scale.